I'm going to present you the project called Hi-Lite, which is partly funded by the French government under the systematic competitiveness cluster, and whose goal is to build a verification toolkit for unit test and unit proof. And I'll save the nifty acronym for Hi-Lite until the end of my presentation, when it's easier to understand. So I'll start with the context. Right now, if you're developing avionics software, you have to comply with a standard called DO-178B. And this standard mandates a certain number of verification activities, among which a lot of testing. And we are interested in unit testing here, although the standard doesn't mandate you that you do unit testing per se. It mandates that you do requirement-based testing, and unit testing is a way to implement this requirement-based testing. So what the standard says, it says that you must start with high-level requirements on the left, which is a pile of documents in natural language. And you extract from these high-level requirements, low-level requirements, which, as their name indicate, are much more detailed. And they are so much detailed that you can, in fact, extract some codes here, individual functions from these low-level requirements. And on the other side, you can extract unit tests, which are going to implement the requirements-based testing, so that at the end you can match, you can exercise the test against the codes and check that the coding phase didn't introduce any errors with respect to your requirements. And of course, this is a quite heavy process, quite costly. So some people at Airbus, in conjunction with people at CEA, have come up with an idea of unit proof to replace some of this unit testing. So what they do is that they start with the low-level requirements here, like before. And on one side, they develop the C code for these low-level requirements. And on the other side, they extract contracts in some logical language, which are composed of preconditions, which state what the subprogram is assuming from its calling environment, and postcondition, which state what the calling environment is assuming from the procedure when it returns. And from this code and these contracts, you can feed them to a tool which generates verification conditions, so formulas that must hold, mathematical formulas that must hold for the code to implement these contracts. And afterwards, you can feed these formulas to a prover, automatic prover, to get proofs. And if you follow this process, you get a unit proof of some of the properties you wanted to test. And you may prefer to go this unit proof way instead of the unit testing way if it's less costly. So that's been something used by Airbus, for example, on the A380 software. And I'll talk about this, the tool that helps them do that. So this was quite pioneering from Airbus to do so in the context of the DO-178B, the current standard. But in fact, there will be a general framework for doing this formal analysis instead of testing, for example, in the next standard. So the upcoming standard is the DO-178C, and it defines what is a formal method applied to the avionics software development. It defines it this way. You need to have a formal model, so a mathematical description of your problem. And in the example just I showed before, this is both the code, so you need a formal model for the programming language and the code you write, and a formal model for the contracts, so you need a logical language for describing your properties. And on this formal model, you can perform some formal analysis, so mathematical analysis based either on deductive methods, model checking, abstract interpretation, so known techniques. And these formal analysis extract some proofs of some of the properties you want to prove. And altogether, these are the formal methods that will be allowed on the software developments in avionics. So the good news is that if today some of you have knowledge and formal analysis that you develop on some formal models producing proofs, you will be able to apply them in the context of avionics software development in the near future, and especially if it helps saving some testing and so cutting on costs, ultimately. So that's the bet we have for Project Hi-Lite. And we start with the problems. So there are some problems with the approach that Airbus has taken with unit proofs. And these are the following. First, it requires a certain expertise to write the contracts I showed you, which are usually more complex than the small snippets I put in my slides. Because it's not the code, it's not some code, it's some logical assertion in some logical mathematical language. And usually to carry on the proof, you need some expert knowledge of the prover also. Since these contracts are written in some mathematical annotation language instead of the code, there's both duplication, so the testing cannot be done on these annotations. So you need to translate things both for testing and for the proof. And there's also isolation, so you cannot combine the results you would get by testing and proofs. So dynamic and static verification. Since it's a different language, there's a potential for confusion, because the same expression of the language, Boolean expression of the language, doesn't mean quite the same thing in the code and in the annotations, especially with respect to runtime errors. And researchers like Patrice Chalin have carried experiments with programmers, benchmarks on programmers, and they have shown that the confusion arises. And it's a real problem to mix these two semantics. And finally, and maybe it's the more important part, the debugging part. Since it's an annotation language in pure logic, you cannot debug these contracts. You cannot either execute them, debug them, and then run the proof as you would run a program. And this part is certainly the most damaging for putting this in an industrial context. And so the solution we have is to center our work around a central executable annotation language. So this thing in the middle. Why? Because since it's an annotation language, you can feed it to formal verification tools, so you still have a contract. And since it's executable, you can test it and debug it. So some Boolean expressions of the programming language that are used for expressing your properties. And since it's inside the language, the programming language, you can use your usual static analyzers on this language to both understand the annotations and maybe check some of them and issue warnings, errors. On the other side, static analyzers, at least some, are good at inferring properties, and you could express them in this same executable annotation language. Of course, most of these annotations are expected to be written manually by the user. And although it's outside the scope of Hi-Lite, this opens the possibility to generate these annotations together with the code, since they are at the same level, from models, so higher level languages. So to put it more concretely, here is an example of a contract on some very simple example, a squared function, as it will be allowed in the next version of Ada 2012, I should say, the marketing. And so the first thing we see here is the contract. So pre and post introduce these preconditions and post conditions as Boolean expressions in the language. So you can here execute them because the compiler will insert them as special assertions at the appropriate points. And this opens the possibility of doing unit testing on these or unit proof. Right? Next step is to introduce test cases which do not have this same executable semantics. That is, the compiler is not going to introduce anything for these test cases, but they're expressed the same way. So you have different names. So for example, requires corresponds to a precondition and ensures to a post to avoid mismatch. But they likewise express properties that you expect in entry and exit of functions as Boolean expression in the language. And these test cases, you can exploit them either in a testing framework to write test procedures and check that these test procedures cover your test cases, or you can prove some of them. And then you see that there's finer grain integration between what you can prove, what you can test at the subprogram level, and all expressed in the same specification language. So the project objectives globally are to facilitate proof of safety, security, and any kind of user properties of interest. And around one language of assertions I showed, these for integrating the results of testing, proof, formal proof, and static analysis. And we want to do that for a subset of C and a subset of Ada. And we have tools to do that. I'll show you later. And also to allow mixed Ada and C code, which is the norm in current days developments. in critical software. The project partners are the following. Adacore, Altron Praxis, CA, List, and INRIA Proval are providing the basic blocks for this technology. And Altron Praxis, EADS, Thales will be the first users of the technology and will build these cases using this technology. So just a quick sketch of interaction. So although I'm not going into the details, the yellowish bubbles are the languages. So you might spot Ada, the Spark subset of Ada, the C language at the bottom left corner. And the boxes are the tools that already exist and have already an industrial basis. So the blue tools are the compilers and static analyzers by Adacore. The Pharmacy orange box is the platform developed by CA List for analysis of C code. The purple tools tool chain is the formal proof tool chain by Altron Praxis. And the green boxes is the formal proof tool by INRIA. And the first thing I think when I see one of these diagrams, the first thing I experiment is fear. Fear as a user that I might be stuck in this web of interactions. And hopefully this is not the case, because what I'm showing you here is the engine. And really the interactions here occur at this level, at the level of source code, what the user really understands. So Ada source code and C source code. And all the machinery is hidden, will be hidden under our two IDEs that we develop at Adacore. And the second impression that I have when I see this kind of diagram is also fear. Fear as an engineer that there might be some mistranslation in this kind of game of Chinese whispers. And téléphone arabe in French. And I had to look it up. and there really the GPL status of all these tools helps. And by the way, I didn't mention it, but all these tools are GPL. Oh. And the other thing that is as important. So I'll detail that later. And so, as important as the GPL status of all these tools is the fact that they are all industrial tools. And in the following, I'm going to describe for all these groups and tools a quick history of these tools. First, to give you an idea of the industrial application of these tools. And second, to show you the history that led to GPL or free license for these tools, as some were born into GPL or free license, and some were converted to it. So to start with, Altron Praxis developed this language and tools that are called Spark. So Spark is a formal language for verification. And there's a set of tools that ship with Spark. So there's a static checker, static analyzer, to make sure that everything is initialized and that enforces a special initialization policy on the code. There's a VC generator, so some tool that generates verification conditions, formulas to prove. And there are provers, automatic and manual provers. So it all started around the 80s in Southampton University. So it's some academic world that started it all. They started a company quite quickly. And this led to various projects, industrial projects. So like in 1996, this Chalice is some ship helicopter information system of the UK Royal Navy, where they applied static checking, the static checking part, and the proof of runtimers. And to give you an idea of the size of these systems, I put the number of verification conditions, so formulas to prove. And this system was 10,000 VCs. More recently, in 2003, the NSA mandated Praxis to develop a small, to redevelop a small biometric system called Tokeneer to serve as a proof of concept. And it was 2,500 VCs. And by the way, this Tokeneer security system is open source today and available on the web. Since 2005, in fact, I got the right figures now, Praxis has been developing this project IFACTS, which is the next version of air traffic control system for the UK air control traffic, and which is 1,025, the exact figure today, VCs. where they check also the static properties, static checking, and absence of runtime errors only, so no user properties. And since 2008, we're doing joint development under a free license. So it was quite a long time before they joined the open source community and free license community. So they did that because they felt that the language and tool set was a bit stuck in its niche markets, and they needed to open it. And so we decided to go with them and find more opportunities. And we convinced them that the right way to do it was to be GPL. And since then, there have been releases starting in 2009, free license releases every year, and which have fostered a lot of interest both in academics and in some industries. Next is Ada Core. So we build tools for critical software development, mostly in Ada, but also in C, C++, and a little bit in Java. And we have R&D projects in the fields of formal methods, like you see here, modeling, emulation, and I forgot to say qualification of tools. So at the bottom of this time arrow, I put the evolutions of the Ada language, which has evolved quite a lot. And the next version of Ada, 2012, has nice things for specification and verification, like contracts, invariants, quantifiers. So all of these executable that can be exploited either for dynamic verification or for static verification, of course. And Ada Core was born in GPL world. So from the start, it was born on the GNAT compiler based on GCC. And since then, all our tools, so GPS in 2000, our main IDE, CodePeer, a tool that was previously developed for some years by SoftCheck, an American company, as closed source, and which they have agreed to co-develop with us now in GPL. I've mentioned already the Spark tool set, which is GPL since 2008 also. And today we have a lot of customers in avionics, space, military, transportation, health, and all our tools are GPL. So, and we're really pushing it because it helps in our market, and it helps in the kind of collaboration that I'm showing here. Next is INRIA tools. So the Y and AlterGo tool chain for formal verification. So Y is first an intermediate language, so a bit like Spark, and maybe you saw in my previous diagram that the Spark tool chain for formal verification was paralleled by an INRIA tool chain, which does approximately the same things. So Y is a language, and it's also the verification condition generator, the tool that generates verification conditions. And AlterGo is the prover, the SMT prover. And so, like many teams at INRIA, they're committed to free software. So they started with Y in GPL in 2000. And all their tools since then have been either GPL or CCLC licensed. And so there was Krakatoa for verification of Java programs, Caduceus for formal verification of C programs. It has been superseded by the Pharmacy platform, which I'll discuss later, which embeds the Y and AlterGo tools for verification of C programs also. And right now, AlterGo, since 2009, is being qualified for used by Airbus in its production chain. So the prover is being qualified for real use in avionics software development. And this is still evolving. So for example, in 2011, there will be a major release of the language and tools set that comes with it. And last is the CEA, which comes with its platform for verification of C codes and analysis in general of C programs. So one of the things that it offers is formal verification through these Y and AlterGo tools that are embedded. So it started in 1995 with the tool Caveat, which was a product of the collaboration between Airbus and CEA. So not open source at the time, not free software. And Airbus qualified this tool for its use on the A380 in 2005. In 2006, they started together, as well as the INRIA, the Pharmacy tool set, which embeds the Y and AlterGo, which is a successor of both the Caveat tool here and Caduceus from the INRIA. And they've come to realize quickly that their target, which was researchers both in industry and academics, would be more interested to use this tool if there was a free license. And so they came to release Pharmacy with a GPL license since 2008. That was the first release. And this has been quite a successful strategy so far, from what I see in the Pharmacy mailing list. And for example, in 2 weeks' time, I'll be in Germany for a 2-day tutorial organized by Fraunhofer Institute, which is a German research institute, to push forward the to push forward the application of Pharmacy in some industrial domains like railway. And just to finish this talk, I wanted to show the final picture of the openness versus closeness of all of these tools and projects, because they are not. That doesn't mean that because you have a free license that everything is open, in particular the developments. So all of these tools have free licenses. Most of them, but one, have every year a GPL or free license release. Some of them, so mostly GCCignat and Pharmacy, have an open bug tracking system. For the tier 2 other here, in fact, it's an academic only bug tracking system which is open. Most of them have an open mailing list. So for Spark, it's one way. So people can send mail, but they don't see all the conversations. For some of these tools, you have an open version control system. And finally, the development is really open only for GNAT GCC. And mostly, I must say, because there the interest is great by many companies to share the work, whereas in many of these other tools, this could be done if there was external interest. But as you might guess, these specialist tools are not developed, are not of interest to many people outside the people who are currently developing them. And so, for example, Spark is co-developed right now between AdaCore and Praxis. And Pharmacy has a plugin platform, so you can develop your own plugins and put it inside their common framework. And so I'd like to say that for Hi-Lites, we'd like to open as much as possible. And we try to push it forward, for example, by discussing all the technical features and challenges on the public mailing list, to which everybody can possibly subscribe. And we try to put all our intermediate documents, all our intermediate presentations, either on the website or in the open version control system. So we try to open it as much as possible. So for all the new tools that do all this translation between languages, and as you can see, everything is freely licensed anyway. So we welcome, in fact, contributions and collaborations around this Hi-Lite project. So in case you're interested by such a collaboration, please come see me at the break and we can discuss. Thank you.